A heavy steel drawer rolls open on precision tracks. Inside, thick, pitted slabs of fossilized bone rest on white foam. These are armor plates from the late Triassic. They formed roughly 235 million years ago. The metal drawer clicks shut. Dust clings to the grooved bone. If you walk through quarries from this period, the raw fossil counts are glaring. For every single dinosaur bone hauled out of the rock, we find dozens of these armored crocodile relatives. Some of these animals grew to the length of a large pickup truck. The landscape was already conquered. Dinosaurs were a rare footnote. This is a synthesis, built from multiple documented cases. If early dinosaurs were smaller, less diverse, and outnumbered by their crocodile-line cousins, how did they eventually inherit the Earth-Permian-Triassic boundary, about 252 million years ago? Reconstruction, constrained by isotopic clocks and global ash deposits. We picture a world suffocating under a poisoned sky. There is no asteroid impact here. The devastation comes from within. Massive volcanic fissures tear open across the northern reaches of the supercontinent Pangea. It is not a single, sudden explosion. It is a relentless flood of molten rock. The eruptions pour out continuously over hundreds of thousands of years. Thick layers of lava spread across immense distances. Millions of cubic kilometers of basalt smother the land. SRC01, Journal article. 2014. The physical lava is only the beginning of the end. The eruptions vent colossal volumes of carbon dioxide and sulfur dioxide high into the atmosphere. The chemistry of the air breaks down. Sulfur dioxide mixes with atmospheric moisture. It falls back to the earth as acidic rain. The rain burns the leaves off ancient trees. It strips the soil of vital nutrients. It pollutes the freshwater rivers and shallow lakes. The global forests wither. SRC01, Journal article. 2014. Carbon dioxide acts as a heavy blanket. It traps the sun's heat against the surface of the planet. Earth's average temperature climbs higher than most living organisms can tolerate. The oceans suffer equally under this rapid warming. As the seas absorb the heat, the water loses its dissolved oxygen. Huge stretches of the ocean become stagnant and dead. Marine ecosystems that took millions of years to build simply disintegrate. The fossil record shows a staggering loss of biodiversity. Nearly every branch of the tree of life is pruned back to the trunk. SRC01, Journal article. 2014. We cannot tell the exact day this extinction started from this evidence. What the rocks do support is a rapid, catastrophic collapse of global ecosystems. Life on Earth does not end completely, but it comes perilously close. The survivors inherit a barren, broken landscape defined by scarcity. The slate is wiped clean. A new geological period begins on this empty stage. We call it the Triassic. SRC01, Journal article. 2014. Present day, microscopy lab. Silver tweezers lower a small glass slide onto a microscope stage. A dial turns. The focus racks through a suspended field of ancient dust. The light catches tiny, golden brown spheres. They are spores. We track the death and recovery of global forests by counting what the wind left behind. In rock layers from before the extinction, we see a rich mix of pollen. This pollen belonged to massive seed-bearing trees. But near the 252 million year boundary, that diversity vanishes. The tree pollen drops away. In its place, the slides are flooded with fern spores. SRC01, Journal article. 2014. Extracting these spores takes careful chemistry. Researchers dissolve chunks of ancient sedimentary rock in strong acids. The minerals melt away. Only the toughest organic materials survive the acid bath. What remains is washed, filtered, and mounted on glass. Under the lens, a dramatic story unfolds in microscopic detail. The sudden spike in fern spores is a global signal. We find it in rocks from Europe to Antarctica. It is the signature of a devastated world trying to heal. SRC01, Journal article. 2014, Early Triassic, about 251 million years ago, reconstruction, constrained by the spore counts. We picture a desolate landscape slowly turning green again. The great forests are gone. Their decaying root systems can no longer hold the soil together. When seasonal rains finally fall, rivers choke with mud. They wash freely across the open plains, burying everything in thick sediment. But life holds on. Ferns are pioneer species. They require very little to take root in disturbed, damaged ground. They reproduce rapidly through spores carried on the wind. SRC01, Journal article. 2014, vast, low carpets of ferns spread across the empty mudflats. They blanket the shifting river banks. They stabilize the loose dirt with shallow root networks. For thousands of years, this simple plant community dominates the recovering world. This is the fern spike. It is a biological bandage applied to a scorched planet. Small insects and surviving reptiles shelter beneath these low fronds. They are the refugees of the old world. They are stepping into an empty arena. SRC01, Journal article. 2014, The Triassic begins in relative silence. The massive apex predators of the previous era are missing. The towering canopy trees are gone. The ecological niches are wide open and waiting. The stage is set for a profound evolutionary race. Different groups of surviving reptiles will spread across the great supercontinent. They will adapt to extreme heat and harsh seasons. For the next 50 million years, they will compete for dominance over the land. Somewhere in this quiet, recovering landscape, the ancestors of the dinosaurs are hiding. SRC01, Journal article. 2014, Present Day, Geological Map. A stylus traces the outline of a massive landmass on a digital screen. This is Pangea. It is a map of the world during the Triassic. Tectonic plates have slowly pushed almost all dry land together. One unbroken supercontinent stretches nearly from pole to pole. A single, vast global ocean surrounds it. Geography creates destiny. Moisture evaporating from the surrounding ocean cannot easily reach the deep interior. The rain falls mostly near the coasts. By the time weather systems push inland, the clouds are incompletely dry. Paleoclimatic consensus. The immense scale of Pangea disrupts normal global air currents. Because the vast landmass heats up and cools down much faster than the ocean, the interior experiences wild temperature swings. The summers are intensely hot. The winters deep inland can drop near freezing. Coastal mountain ranges act as massive atmospheric walls. They force moist ocean air to rise and drop rain on the seaward slopes. The land on the other side is left in a permanent rain shadow. This geographic reality sets the stage for a hostile global environment. Paleoclimatic consensus. Present day, field site. A rock hammer chips away at a crumbling, reddish-brown cliff face. Dust falls to the desert floor. We are looking at a cross-section of deep time. The layers in this stratigraphic column run like horizontal stripes across the Badlands. A geologist holds a color chart against the fresh rock to record its hue. The striking red color comes from oxidized iron. It is ancient rust. We are looking at paleosols. These are fossilized soils that formed on the surface of Pangea millions of years ago. Stratigraphic record. Close inspection of the rock face reveals deep, V-shaped fractures filled with lighter sand. These are preserved mud cracks. They formed when wet earth baked and split under a blistering sun. Deeper in the trench, the hammer taps against hard, pale lumps encased in the red dirt. These are carbonate nodules. They form in soil only when evaporation heavily outpaces rainfall. As intense heat draws groundwater upward, it evaporates, leaving dissolved minerals behind to harden. Geologists measure the depth of these nodules to estimate ancient precipitation. The math reveals a startling lack of water. The rocks tell a story of extremes. Gen. Stratigraphic record, moving higher up the cliff face. The red soils give way to thick layers of yellow sandstone. The texture here is entirely different. Fine, rounded grains of quartz are stacked in sweeping, diagonal lines. This structural pattern is called crossbedding. It is the undeniable signature of wind-blown deposits. We are standing inside a petrified sand dune. These sweeping lines record the exact angle of the ancient wind. They prove that vast, migrating deserts swallowed entire regions of the supercontinent. There was no water here to move sediment. Only the wind. Gen. Stratigraphic record, Middle Triassic, about 240 million years ago. Reconstruction, constrained by these cracked soils and petrified dunes. We picture a brutal, unforgiving interior. The sun beats down on a vast, rocky plain. There is little shade. The heat is relentless. For much of the year, the riverbeds are dry scars cutting through the dust. The wind pushes loose sand into migrating dunes that slowly bury struggling stands of low vegetation. Survival here requires extreme endurance. Animals must travel long distances to find shrinking pools of stagnant water. They are pushed to their limits. Gen. Paleoclimatic consensus, then. The season breaks. The shifting heat of the massive continent draws ocean air inward. The sky darkens. The monsoons arrive. Rain falls in violent, torrential sheets. The baked earth cannot absorb the deluge fast enough. Dry washes transform instantly into raging, muddy torrents. Flash floods sweep across the flatlands, carving new channels and tearing up the brittle soil. The water brings sudden, explosive life. Dormant seeds sprout rapidly in the mud. Shrubs and tough ferns blanket the riverbanks in brief. Chaotic explosions of green. Animals must exploit this narrow window. They drink, feed, and reproduce before the water vanishes again. Gen. Paleoclimatic consensus. The plant life must also adapt to the scarcity. Water-loving spore plants retreat to the dampest river margins. On the open plains, seed-bearing plants gain the upper hand. Early conifers and tough cycads take root. Their seeds feature protective coats. They can lie dormant in the baking dust for months, simply waiting for the monsoon's trigger. Their leaves are tough and narrow, minimizing water loss under the punishing sun. It is a harsh reality. Gen. Paleoclimatic consensus. We can't tell exactly how hot Pangea's summers became from this evidence. What it does support is a cycle of severe, extended droughts. This oscillating climate dictates the terms of evolution. Animals tied strictly to standing water face a grim reality. Large amphibians struggle. They must lay their jelly-like eggs in fresh water, leaving them entirely dependent on shrinking seasonal pools. When the pools dry out, a generation is lost. But reptiles possess a distinct evolutionary advantage. Their bodies are covered in watertight scales that prevent fatal dehydration. More importantly, they lay amniotic eggs. Gen. Evolutionary consensus. These eggs feature a protective shell that locks moisture inside. The developing embryo carries its own private bond. This single adaptation severs the absolute tie to standing water. It allows reptiles to march inland, crossing the dusty plains and establishing themselves in the harsh interior of Pangea. They can lay their eggs in the dry soil and walk away. Gen. Evolutionary consensus. Any creature hoping to dominate this world must be built for austerity. They must endure blistering heat, survive the creeping drought, and exploit the sudden, violent floods. It is a crucible of natural selection. And out of this crucible, a spectacular array of new predators and armored herbivores begins to rise. They will radiate across the scarred landscape. They will rule the Triassic world long before the first dinosaur ever casts a shadow. Gen. Evolutionary consensus. Present-day, museum collections. The heavy steel door of a specimen cabinet rolls open on precision tracks. Inside, resting on white foam, are thick slabs of fossilized bone. They are roughly rectangular, covered in pitting and deep grooves. Some are flat, while others curve sharply to form rigid spikes. A researcher lifts one carefully, resting it against a measuring scale. It is heavy and dense. These are not internal skeleton bones. They are osteoderms. They are massive plates of armor that formed within the skin of an ancient reptile. When we arrange them together on a table, they interlock, forming a nearly impenetrable shield. The sheer volume of these armored plates in Triassic rock layers tells a clear story. The herbivores of Pangea were heavily defended. SRC 05, Journal article. 2008, Late Triassic, about 235 million years ago. Reconstruction, constrained by the interlocking osteoderms and squat skeletal proportions. We picture a low, sprawling beast moving slowly through the ferns. This is an aetosaur. It resembles a heavily armored reptilian armadillo. Aetosaurs belong to a larger group known as crocodile-relatives, or crocodile-relatives. They are the distant, heavily modified cousins of modern crocodiles. The animal's body is entirely encased in rows of bony scutes running down its back and tail. Sharp spikes jut from its flanks and neck, deterring predators looking for an easy meal. SRC 05, Journal article. 2008, its skull is remarkably small compared to its bulky body. The snout turns slightly upward, forming a hardened tip perfectly shaped for rooting through the dirt. It moves deliberately, using its snout to unearth roots and tough low-growing vegetation. Its teeth are leaf-shaped, built for cropping plants rather than slicing meat. The aetosaurs are a highly successful design. We find them across the globe, from the red rocks of the American Southwest to the deserts of Argentina. They monopolized the role of armored herbivore long before the evolution of horned or club-tailed dinosaurs. They dominate the low underbrush. SRC 05, Journal article. 2008, Present day, lab workstation. A digital diagram rotates on a monitor. It is the long, narrow skull of a phytosaur. At a passing glance, it looks just like the skull of a modern crocodile. It has the same elongated, tooth-filled jaws and a similar flattened profile. But a crucial detail separates them. The cursor highlights the nasal openings. In a modern crocodile, the nostrils sit at the very tip of the snout. In the phytosaur, the nostrils are positioned high up near the eyes, right in front of the brain case. This is convergent evolution at work. Morphological consensus. Two entirely different branches of the reptile family tree independently arrived at the same biological solution for hunting in shallow water. The phytosaurs are not true crocodiles. They are another specialized branch of the crocodile-relatives. Their anatomy reveals their hunting strategy. Morphological consensus, late Triassic, about 235 million years ago. Reconstruction, constrained by the high nasal placement and elongated jaws. We picture a massive predator waiting in the muddy shallows of a seasonal river. The phytosaur is nearly entirely submerged. Only its size and the high nasal crest break the surface of the water. It can breathe and watch the shoreline while remaining practically invisible. Its powerful, muscular tail sweeps slowly, holding it steady against the current. The jaws are lined with conical teeth near the front for gripping slippery prey, and serrated teeth further back for slicing meat. Morphological consensus. When a thirsty animal approaches the water's edge, the strike is explosive. The phytosaur lunges upward, driven by the thrust of its massive tail. The jaws snap shut with bone-crushing force. Phytosaurs dominated the freshwater ecosystems of the Triassic. They grew to massive sizes, roughly the length of a large pickup truck. They were the undisputed apex predators of the rivers and lakes. If early dinosaurs approached the water to drink, they did so at tremendous risk. The shallows belonged to the phytosaurs. Morphological consensus. The dominance of the crocodile-relatives extended far beyond the water. Late Triassic, about 235 million years ago. Reconstruction, constrained by deep, powerful skulls and robust limb bones. We picture a terrestrial nightmare. This is Postosuchus. It is a Rorschackian. Yet another terrifying branch of the crocodile family tree. It is built entirely for hunting on dry land. It possesses a massive, boxy skull filled with curved, serrated teeth designed for tearing large chunks of flesh. Its neck is heavily muscled, allowing it to rip struggling prey apart. Morphological consensus. Unlike a modern sprawling crocodile, Postosuchus stands tall. Its legs are positioned in a semi-erect posture, bringing its belly off the ground. This posture allows for efficient, powerful strides across the dry plains. It is huge, heavily built, and undeniably lethal. It moves through the scrublands searching for armored aetosaurs or stray herbivores. Postosuchus and its Rorschackian kin occupied the very top of the terrestrial food chain. They were the apex hunters of Pangea. Morphological consensus. We cannot tell if Postosuchus hunted in packs from this evidence. What it does support is a solitary apex predator adapted perfectly for terrestrial hunting. The Triassic world was not a blank canvas waiting for dinosaurs to arrive. It was a crowded, brutal, and highly competitive ecosystem already conquered by massive, highly specialized reptiles. The crocodile-relatives had claimed the rivers. They had claimed the role of armored tanks. They had claimed the top predator niches on land. They were diverse, abundant, and terrifyingly effective. SRC 05, Journal article. 2008. If these towering monsters ruled the land and the water, where are the dinosaurs present day? Ishigalasto Provincial Park. The Argentine wind howls across the Valley of the Moon. The Badlands here are stark, stripped of vegetation, exposing alternating bands of grey, white, and red rock. A field crew works slowly under the harsh sun. A paleontologist brushes away loose sediment from a crumbling slope. A small, curved piece of bone emerges from the rock. It is fragile. The crew applies a liquid consolidant to harden the fossil before attempting to move it. They meticulously map the exact layer where this bone rests. This is the Ishigalasto Formation. Radiometric dating of volcanic ash layers places these rocks in the late Triassic. It is here, in these desolate hills, that we find the scattered fragments of the very first dinosaurs. SRC 02, Journal article. 1993. They do not look like the giants of popular imagination. Late Triassic, about 231 million years ago. Reconstruction, constrained by nearly complete skeletons found in the ash beds. We picture a creature built for the shadows. This is Eoraptor. Its name means dawn thief. It is small, stretching roughly 1 meter from snout to tail, about the length of a large dog. It weighs no more than a few kilograms. It is not an apex predator. It is a marginal opportunist. It moves quickly on two long, slender hind legs, using its stiff tail for balance as it darts between the cycads. SRC 02, Journal article. 1993. Its hands feature grasping fingers with sharp claws, perfect for snatching insects, small lizards, or perhaps rooting through low vegetation. Its teeth are a mixed toolkit. The front teeth are slightly curved for gripping meat, while the teeth further back have small serrations suited for cropping plant material. Eoraptor is an omnivore, scratching out a living wherever it can find calories. It is the baseline model. It represents the starting point from which all later dinosaurs will evolve. And in this landscape, dominated by massive, armored crocodile cousins, it survives by being fast and staying out of the way. SRC 02, Journal article. 1993. Present day, prep lab. Inside a bright, sterile preparation lab. The high-pitched whine of an air scribe cuts through the silence. A preparator looks through a magnifying visor, using a tiny pneumatic needle to vibrate away the last crust of hard rock matrix from a fossil pelvis. The bone is dark and well preserved. It belongs to Herrerasaurus, a slightly larger predator found in the same Argentine rocks as Eoraptor. The preparator works carefully around a specific hollow in the bone. It is the hip socket, where the thigh bone once connected. As the rock falls away, a defining anatomical feature is exposed. SRC02, Journal article. 1993. There is a hole right through the center of the socket. Present day, anatomy analysis. A 3D diagram rotates on screen, comparing a sprawling lizard pelvis to the pelvis of Herrerasaurus. In a typical sprawling reptile, the hip socket is a solid wall of bone. The femur, or thigh bone, sticks straight out to the side. The animal walks with its belly low, expending massive amounts of muscular energy just to keep its body off the ground. But the dinosaur diagram shows a profound anatomical shift. The hip socket, the acetabulum, is completely open. It is a perforated window. SRC02, Journal article. 1993. Because the socket is open, the head of the femur turns sharply inward. It locks firmly into the hip, acting like a pillar supporting a heavy roof. The legs are brought directly underneath the body. The animal stands upright. This is the mechanical definition of a dinosaur. This single anatomical innovation changes everything about how the animal moves. It no longer swings its spine from side to side in a sprawling gait. The upright stance supports the body's weight efficiently. It frees the lungs to breathe deeply even while running at a full sprint. It is a masterpiece of biological engineering. SRC02, Journal article. 1993. We can't tell what color Eoraptor was from this evidence. What it does support is a small, agile body built specifically for highly efficient running. This upright posture allows early dinosaurs like Herrerasaurus to become active, swift-moving hunters. Herrerasaurus is larger than Eoraptor, reaching several meters in length, roughly the size of a mid-sized car. It is a dedicated carnivore. Its deep skull houses sharp, serrated teeth, and its powerful hind legs make it a formidable sprinter. Its grasping hands feature large claws to restrain struggling prey. It hunts the smaller reptiles and early mammal relatives that scurry through the underbrush. SRC02, Journal article. 1993. But even with this remarkable upright stance, the dinosaurs are not conquering the world. They remain rare. In the fossil record of the Aeshigalasto Formation, the remains of early dinosaurs make up only a tiny percentage of the total animal fossils discovered. The vast majority of the bones belong to other groups of reptiles and massive rhynchosaurs, squat, pig-like herbivores with strong beaks. The dinosaurs are present, but they are hiding in plain sight. They are a minority group, testing a new way of walking on a harsh and dangerous continent. SRC02, Journal article. 1993. Their upright stance is clearly an advantage. But is it enough to overthrow the massive, ruling crocodile cousins? The answer requires mapping the exact dimensions of evolutionary success. Present-day, data workstation, a cascade of coordinate points floods a monitor. A researcher builds a mathematical map of evolutionary success. The screen displays a three-dimensional graph. This is a morphospace. It is a visual representation of how different animal bodies are shaped. The data points represent dozens of archosaur skulls from the Triassic period. The computer quantifies snout length, skull depth, and jaw mechanics. It translates bone into cold, hard numbers. This is a study of morphological disparity. It asks a simple question. Which group of animals explored the widest variety of body plans? SRC05, Journal article. 2008. The graph plots early dinosaurs in blue. It plots crocodile-line Crurotarzans in red. The result is unambiguous. The blue points cluster tightly together in a small corner of the graph. Early dinosaurs all look remarkably similar. They are mostly small, bipedal, and lightly built. But the red points explode across the screen. They spread into almost every available corner of the evolutionary map. SRC05, Journal article. 2008. The data reveals that crocodile line reptiles were doing everything. They were giant, armored root diggers. They were long-snouted ambush hunters. They were towering apex predators running across the dry plains. They possessed a staggering diversity of shapes and sizes. Dinosaurs, by comparison, were anatomically conservative. They were locked into a single, highly specialized body plan. The math shatters a long-held myth. SRC05, Journal article. 2008. For decades, popular narratives claimed that dinosaurs possessed a superior design. The assumption was that an upright posture gave dinosaurs an overwhelming advantage. People believed this allowed them to rapidly outcompete sprawling reptiles and conquer the Triassic world. The data shows this is entirely false. SRC05, Journal article. 2008. We can't tell exactly why crocodile relatives evolved more diverse shapes from this evidence. What it does support is that dinosaurs were an anatomical minority group. Present day, museum comparison. We can look at raw fossil counts from Triassic rock layers. The Chinle Formation in North America provides a perfect example. When paleontologists tally the bones hauled out of the quarries, the disparity is glaring. For every dinosaur bone found, there are dozens of phytosaur and aetosaur bones. Crocodile line reptiles are universally abundant. They are the defining animals of the ecosystem. Dinosaurs are a rare footnote in the fossil record. They are vastly outnumbered, outsized, and out-diversified. SRC05, Journal article. 2008. Late Triassic, about 225 million years ago. Reconstruction, constrained by bonebed counts and disparity mapping. We picture a world where dinosaurs survive entirely on the fringes. We see Saturnalia, another early dinosaur. It walks on long legs. It possesses a slightly longer neck and a small head. Its teeth show adaptations for eating both plants and small animals. It is a distant, early ancestor of the giant sauropods that will one day shake the earth. But right now, Saturnalia is roughly the size of a wolf. It scurries through the ferns. It is constantly alert. SRC03, Journal article. 1999. It must yield the right of way to massive, armored aetosaurs slowly pushing through the brush. It must flee from towering Rorschackian predators patrolling the open ground. It must avoid riverbanks where phytosaurs wait in ambush. For 30 million years, this is the dinosaur experience. They are not the masters of the universe. They are the underdogs. They exist in the shadows of giants. They utilize their upright speed simply to stay alive. SRC05, Journal article. 2008. The math tells us that dinosaurs were losing the Triassic arms race. They were restricted to small, marginal ecological roles. Meanwhile, their crocodile cousins occupied the thrones of Pangea. If the Triassic ecosystem had continued uninterrupted, there is no reason to believe dinosaurs would ever have taken over. They were locked out. SRC05, Journal article. 2008. So how did the underdogs eventually inherit the Earth? If the answer is not found in their size, their numbers, or their weaponry, we must look deeper. We must look inside the bone present-day histology lab. The sharp whine of a diamond-tipped rock saw cuts through the quiet laboratory. A continuous stream of water cools the spinning metal blade as it slowly bites into a dark, mineralized cylinder of fossil. It is the femur of an early dinosaur. Paleontology is usually about preservation. But sometimes, to understand how an animal lived, we must destroy a piece of it. The saw slices a thin disc from the bone. A technician mounts the disc onto a glass slide and grinds it down with fine abrasives. They polish it until it is thinner than a human hair. Light can pass entirely through the fossilized stone. We are looking at paleohistology. We are reading the internal architecture of the bone to understand the engine that drove the animal. SRC04, Journal article. 2001, Present Day, Tissue Analysis. A diagram appears on screen, displaying the microscopic view of a crocodile bone under polarized light. The structure is immediately recognizable. It looks like the cross-section of a tree trunk. The bone is marked by distinct, concentric circles. These are lines of arrested growth, or lags. They form when an animal's metabolism slows down or stops entirely due to environmental stress. During the harsh, dry seasons of Pangea, food and water became scarce. The massive crocodile-line reptiles effectively paused their growth to conserve energy. When the monsoons returned, growth resumed, leaving a visible ring. It is a highly efficient, energy-saving strategy for surviving an extreme climate. But it means they grew slowly. It took many years for them to reach their massive adult sizes. SRC04, Journal article. 2001, the view shifts to a thin section of early dinosaur bone. The structure is profoundly different. The neat, tight rings are gone. Instead, the bone is a chaotic, spongy matrix. It is highly vascularized. It is riddled with wide canals where large blood vessels once pumped nutrients through the growing tissue. This is fibrolamellar, or woven bone. It forms only when bone tissue is being laid down rapidly and continuously. SRC04, Journal article. 2001, in a limited sample of early dinosaur bone. This pattern suggests they did not pause. They kept their metabolic engines running hot. They powered through the harsh seasons, sustaining rapid growth rates throughout their early lives. While the giant crocodile cousins hunkered down to wait out the drought, the small dinosaurs kept moving, kept eating, and kept growing. SRC04, Journal article. 2001, Late Triassic, about 231 million years ago, reconstruction, constrained by this highly vascularized bone tissue. We picture Herrerasaurus moving with relentless, nervous energy. It does not bask lazily in the sun for hours like a modern reptile. Its internal physiology demands constant fuel. It is constantly foraging, hunting, and moving. This high metabolic strategy is risky in a world of scarcity. It requires more calories. But it offers a profound evolutionary advantage. Because they grow continuously, early dinosaurs reach sexual maturity much faster than their massive, slow-growing rivals. SRC04, Journal article. 2001, they can produce the next generation in a fraction of the time. While an apex rorschach might take a decade to reach breeding age, a small dinosaur might be ready to lay eggs in just a few years. In the long game of evolution, rapid generational turnover is a powerful weapon. It allows a population to bounce back quickly from environmental disasters. It accelerates the rate at which advantageous genetic mutations can spread through a population. SRC04, Journal article. 2001, we can't tell if early dinosaurs were fully warm-blooded from this evidence. What it does support is that they grew continuously and rapidly compared to their rivals. This physiological divergence is the invisible margin between the two groups. The crocodile-line archosaurs dominated the landscape through sheer size, heavy armor, and energy conservation. They were perfectly adapted to rule the stable, albeit extreme, climate of the Triassic. The dinosaurs remained small, utilizing their upright posture to scavenge calories and their fast metabolism to grow and breed quickly. They were living fast on the fringes of the ecosystem. SRC04, Journal article. 2001, for 50 million years, this uneasy balance held. The massive, slow-growing giants ruled. The small, fast-growing opportunists survived in the shadows. Neither side was destined to outcompete the other. But the rules of the game were about to change catastrophically. The supercontinent of Pangea was beginning to tear itself apart. The internal engines recorded in these bone slices would dictate who survived the coming fire. Present day, stratigraphic section. A geologist's hand rests firmly on a sheer rock wall. Fingers trace a distinct, dark line. It cuts horizontally through the pale sediment. We are looking at another boundary in deep time. This is the Triassic-Jurassic boundary. High precision dating places this layer at roughly 201 million years ago. Below this line, the rock layers are packed with fossils. We find the armor of aetosaurs, the massive skulls of phytosaurs, and the serrated teeth of raugekians. But move your hand just a few centimeters higher. They are gone. The massive crocodile-relatives vanish abruptly from the fossil record. The rock above the line is empty of their bones. Gen. Stratigraphic record. End Triassic, about 201 million years ago. Reconstruction, constrained by stratigraphy and global volcanic deposits. We picture Pangea ripping apart. The immense tectonic plates that formed the supercontinent begin to shift. They pull away from each other. This opens a massive rift that will eventually become the Atlantic Ocean. As the crust tears, unthinkable volumes of magma surge to the surface. It is the Central Atlantic Magmatic Province. It is one of the largest volcanic events in Earth's history. It triggers a catastrophic chain reaction. This devastation mirrors the event that started the Triassic. Gen. Geological consensus. Massive quantities of greenhouse gases flood the atmosphere. Global temperatures spike violently. The delicate balance of the monsoonal climate shatters. Ecosystems that took 50 million years to build collapse in a geologic instant. The top of the food chain is always the most vulnerable. The giant, specialized crocodile cousins require immense amounts of food to maintain their massive bodies. When the herbivores die, the apex predators starve. Their massive size, heavy armor, and slow generational turnover become fatal liabilities. They cannot adapt fast enough to the rapidly changing world. They are completely eradicated. Gen. Paleontological consensus. We can't tell the exact mechanism that spared dinosaurs while killing their rivals from this evidence. What it does support is that fast growth and rapid reproduction played a critical role in their survival. Early Jurassic, about 200 million years ago. Reconstruction, constrained by the sudden dominance of dinosaur footprints and fossils above the boundary. We picture a quiet, devastated world slowly cooling down. The giants are dead. Stepping out from the shadows are the survivors. These are the early dinosaurs. They emerge from the margins where they hid for 30 million years. Gen. Paleontological consensus. Their small size meant they needed fewer calories to survive the worst of the extinction. They're highly vascularized. Fast-growing bones allowed them to reach maturity quickly. They bred rapidly and rebuilt their populations even as the world burned around them. Their upright posture allowed them to travel vast distances efficiently to find whatever scarce food remained. They did not conquer the Triassic through superiority or physical combat. They simply endured it. They were physiologically pre-adapted to survive a global catastrophe. SRC 04, Journal article. 2001, they walk onto a barren stage. The rivers are empty of phytosaurs. The plains are free of terrifying raugekians. The ecological niches of the entire planet have been swept clean. For the first time, the dinosaurs face a world without boundaries. The survivors of this fiery crucible will radiate outward. Over the next 135 million years, they will evolve into titans. They will shape the Jurassic and Cretaceous periods. But their success was never guaranteed. It was forged in the brutal heat of Pangea. It was tested against